Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
Okay, so imagine this. The entire AI industry right now is basically playing a game where to build anything meaningful, they first have to sculpt a 100-ton block of marble, and then, after it's done, spend months chiseling away 90 tons of it to make it actually usable. It's insane.
And it's not just inefficient, it's crippling. It's why only the biggest players can even get into the game. We're talking about billions in infrastructure just to get a model to a point where it might be deployed.
But what if you didn't have to do that? What if the marble could basically shrink itself as you're pouring it? That's what some MIT researchers just pulled off. And it's not just a tweak, it's a fundamental rewrite of the AI playbook.
They've effectively found a way to make AI models discover their optimal, efficient shape while they're still learning. We're seeing claims of 4x training speedups, models shrinking by over 90% in terms of their complexity, and still outperforming their born small counterparts. This is a game changer for anyone not named Meta or OpenAI.
That's the part that really got me. This isn't just about making things a little bit faster, it's about making AI accessible and deployable in places we've only dreamed of.
Exactly. And it tackles the dirty secret of modern AI, this train big, shrink later paradigm that's both economically and environmentally unsustainable.
Let's unpack that, because it really sets the stage. We've talked before about how companies like OpenAI and Meta are throwing insane amounts of compute at their models. You mentioned train big, shrink later. What exactly does that look like in practice, and why is it such a problem?
It's the dominant paradigm, and honestly, it's mind-bogglingly wasteful. To get a state-of-the-art model today, you basically have to train a behemoth. Think of GPT-4 or the latest Llama models. These things are colossal, requiring thousands of GPUs running for months, consuming massive amounts of energy.
Right, because the bigger the model, the more parameters, the better it performs. That's been the mantra.
Precisely. But here's the rub. Once you have this incredible, intelligent teacher model, it's far too large, too slow, and too expensive to run on your phone, in your car, or even on a typical laptop. So then you have to embark on a whole second phase, which is dedicated to making it smaller and faster, just so it can actually be used.
So you spend millions to train it, and then millions more to untrain parts of it? That sounds incredibly inefficient. What are the main ways they try to shrink these giants?
There are 3 common techniques. First, pruning. Imagine a neural network as a vast web of connections. Pruning is like going in after the fact and snipping the weakest connections, the ones closest to zero, then fine-tuning to recover any lost accuracy. It's a bit like deleting irrelevant data from a spreadsheet.
Okay.
Second, quantization. This is about reducing the precision of the numbers that represent the model's parameters. Instead of using 16-bit floating point numbers, you might crunch them down to 8-bit or even 4-bit integers. It saves a ton of memory, but there's a trade-off. You often degrade the model's reasoning capability slightly. It's like taking a high-resolution image and saving it as a lower-resolution JPEG.
Makes sense. And the third?
The third is knowledge distillation. This one is particularly expensive. You take your massive, highly trained teacher model and use it to train a much smaller student model. The student doesn't learn from raw data, it learns by mimicking the outputs of the teacher. The researchers at MIT noted that this effectively doubles the training effort.
Double the effort just to get a smaller model? That's the part that feels most like this sculpting a 100-ton block analogy. My immediate question would be, why not just train a small model from scratch? Save all that money and energy.
And that's the question everyone asks. But here's the frustrating quirk of machine learning. A small model, trained from scratch, almost always performs significantly worse than a large model that was trained and then compressed.
Really? Why is that?
Large models have this massive, complex parameter space. They can explore and find optimal solutions in ways smaller models just can't. Small models, when trained from the ground up, tend to get stuck in local optima. They can't see the forest for the trees. So paradoxically, to get a high-performing small model, you first have to pay the astronomical cost of training a massive one.
Wow, so it's like you need the huge canvas to even conceive of the masterpiece, even if you eventually want to put it on a postcard. This compute obsession you mentioned earlier, the meta benchmark, that's all tied into this, right?
Absolutely. Mark Zuckerberg's announcement that Meta was hoarding something like 350,000 NVIDIA H100 GPUs by the end of 2024, that's an infrastructure investment of over $10 billion on the silicon alone. It's a clear signal. Compute is the new oil. The sheer volume of processing power and token spend required to stay relevant has become the benchmark for AI capability. It's environmentally taxing, and it locks smaller startups and academic labs out of frontier AI development. It screams for a disruptive, elegant engineering solution.
Which brings us to this MIT breakthrough. They call it CompreSSM. So instead of sculpting a giant and then chipping away, how does this control theory hack actually work?
It's brilliant. The MIT CSAL team, led by Makram Chahine, essentially said, what if we don't wait until the end to figure out what's important? CompreSSM is an algorithm that completely sidesteps that train big, shrink later trade-off. Their analogy is perfect. It's as if the statue discovers its own efficient shape while the marble is still being poured. The model literally grows smaller and faster while it's actively learning.
That's a huge shift in philosophy. How do they actually do that? How do you know what's dead weight in a neural network while it's training?
That's where the control theory hack comes in. This is where they borrowed from a completely different discipline, typically used in aerospace engineering and robotics to manage dynamic systems. They use a mathematical metric called Hankel singular values.
Hankel singular values. Sounds dense. Can you break that down?
Think of it like this. To safely compress a model, you need to know which parts are truly pulling their weight and which are just taking up space. Hankel's singular values combine two crucial concepts, controllability and observability.
Controllability and observability in an AI model?
Exactly. Controllability asks, how easily can a specific internal state of the model be influenced or excited by the input data? And observability asks, how much does that internal state actually contribute to the final output of the model? By combining these, Hankel singular values give you a mathematically guaranteed ranking of the true energy or importance of every dimension within the model. It tells you definitively which parts are essential and which are just noise.
So it's not just a heuristic guess, it's a mathematically rigorous way to identify what's critical.
Precisely. And here's the kicker, the surprising phenomenon they discovered. The relative importance of these components stabilizes incredibly early in the training process. By the time the model is only about 10% of the way through its training, those Hankel singular values lock into place. They don't change much after that.
Wait, really? So 10% of the way through training, you can already tell what's essential and what's not? That's wild.
It is wild. At that 10% mark, CompreSSM pauses, ranks all the dimensions, and then surgically amputates the dead weight. The remaining 90% of the training process then proceeds on a drastically smaller, faster, and more efficient model.
So instead of training a massive model for months and then compressing it, you train a massive model for, say, a few days, compress it, and then let the smaller, more efficient model finish training for the rest of the month? That's a huge time and resource saver.
Daniela Russ, who's the director of MIT CSAIL and a senior author on this paper, views this as a fundamental paradigm shift. She argues that compression is no longer an afterthought or some post-processing chore. It's an active, dynamic part of the learning process itself. It's about building technology that's both efficient and interpretable, proving that progress doesn't have to mean more. It can mean smarter. CompreSSM turns the model into a self-optimizing system.
That's powerful. But this technique isn't universal, right? It's specifically designed for a certain type of AI architecture.
You're right to point that out. It targets state space models, or SSMs. This is crucial because while transformers dominate the AI landscape today, the T in ChatGPT, SSMs are emerging as a major challenger.
Transformers are everywhere. What makes them so dominant, and why are SSMs considered a threat?
Transformers rely on what's called self-attention. Think of it like this. To understand a sentence, a transformer has to compare every single word in that sentence to every other word. Mathematically, this creates what's called quadratic time complexity, or O of n squared. If you double the length of a conversation, the compute required quadruples.
So if I'm feeding it a long document or a complex piece of code, the computational cost just explodes.
Exactly. It hits massive memory walls and requires enormous key-value KV caches, making transformers incredibly expensive for long documents, continuous audio streams, or extensive code bases. That's why models often have context windows, a limit to how much information they can consider at once.
Okay, so transformers are powerful but computationally hungry, especially with long sequences. How do state space models like Mamba solve that?
SSMs, like the very popular Mamba architecture, are rooted in continuous dynamical systems. Instead of looking back at every previous token individually, they compress the entire history of a sequence into a fixed-size hidden state vector. It's like distilling a whole book down to a single, constantly updating summary paragraph.
So it's not looking back at all the individual words, but rather at a distilled representation of everything that came before.
Precisely. Because they don't need to do that pairwise comparison, they operate with linear time complexity, O of n. If you double the length of the sequence, the compute only doubles, not quadruples. This makes them blindingly fast and incredibly memory efficient. They effectively solve the transformer bottleneck for long sequences.
That's a huge advantage, especially for real-time applications or devices with limited memory. And CompreSSM is specifically designed to turbocharge these already efficient SSMs. What were the actual results, the hard data you mentioned?
The empirical results are incredibly compelling. When they applied CompreSSM to the Mamba architecture, they saw an astonishing 4x speedup in training time. Think about that. A model that took a month to train now takes a week.
A 4x speedup? That's not marginal. That's transformative for R&D cycles.
And it gets better. They achieved mind-blowing dimensionality reduction. The algorithm took a model with a 128-dimensional state space and crushed it down to just 12 dimensions. That's a greater than 10x reduction in complexity, all while maintaining competitive performance.
So smaller, faster, and just as good. But you also mentioned it beats the small model curse?
Yes, this is critical. On a standard image classification benchmark, CFAR-10, a CompreSSM compressed model, reduced to a quarter of its original size, achieved 85.7% accuracy. But a model trained from scratch at that exact same small size only managed 81.8%. That 4-point difference is significant in ML, proving you can get superior performance even when starting with a larger initial structure and then compressing it during training.
So it really does solve that fundamental problem. You don't have to train huge and then post-process, but you still get the benefits of having a larger canvas initially.
Exactly. And to put it in perspective, they benchmarked CompreSSM against a competing state-of-the-art spectral compression technique called Hankel nuclear norm regularization. CompreSSM proved to be more than 40 times faster, while also achieving higher accuracy. It's not just better, it's orders of magnitude better.
Okay, so this is a genuine technical breakthrough. But how does this translate into real-world business implications? What's the big picture here for industries outside of pure AI research?
The ultimate goal of making AI smaller and faster is to untether it from centralized cloud servers. This is huge. Think about it. Right now, if you use a voice assistant or a smart feature in your car, your device is likely pinging a massive data center hundreds or thousands of miles away.
That introduces latency, obviously, but there are other issues too, I imagine.
Oh, absolutely. Latency is just one. You've got privacy risks because your data is leaving your device and going to a third-party server. And there's total reliance on internet connectivity. As Daniela Russ points out, if your car is driving 60 miles an hour, you can't wait 10 seconds for the cloud to tell you what to do.
So this is paving the way for AI that runs locally, on the device itself?
Precisely. This is the realm of physical AI and edge computing. And that brings us to Liquid AI, a spin-out intrinsically linked to this research. It was co-founded by Daniela Russ and other MIT CSAL alumni. They're commercializing these non-transformer architectures, specifically liquid neural networks and what they call liquid foundation models, or LFMs.
Liquid AI. That name sounds like it belongs in a sci-fi movie. What's their vision?
Their mission is to realize this physical AI, intelligence that's interpretable, highly adaptive, and, crucially, compact enough to run locally on pretty much any edge device. We're talking smartphones, drones, pacemakers, industrial robotics. Their models are actually inspired by the brain of the C. elegans roundworm, which has only 302 neurons but can navigate incredibly complex environments. It's about minimalistic intelligence that can still do complex things.
And they're not just an academic project either. They've raised some serious capital.
Staggering capital. After a $37.6 million seed round in late 2023, they closed a massive $250 million Series A led by AMD in late 2024-25. That rocketed them to an estimated $2 billion valuation. This isn't just theory. This is capital markets saying this is real, and it's big.
That kind of funding, paired with this CompreSSM breakthrough, feels like it could really democratize AI.
It absolutely does. If techniques like CompreSSM allow state-of-the-art SSMs to be trained 1.5x to 4x faster and then run locally, it fundamentally changes who can leverage advanced AI. Non-tech Fortune 500 companies, for example. Think about an automotive manufacturer Liquid AI recently helped. By deploying a local model, they lowered their operational costs by 70% simply by reducing their dependency on cloud computing.
70%? That's not just a nice to have, that's a massive competitive advantage.
It completely shifts the value proposition. It decouples intelligence from centralized data centers. The value moves away from the infrastructure providers, like AWS or those massive NVIDIA GPU clusters, and back to the enterprises and the consumers. It paves the way for private, on-premise AI that can be trained natively by hospitals, banks, and manufacturers without paying that hyperscaler tax. It could truly unlock a new era of bespoke, privacy-preserving AI.
That's incredibly optimistic, and the technical side of it sounds solid. But you know us, we have to put a hype check on everything. What are the limitations here? What's the catch?
You're right to ask. The primary limitation right now is architectural. CompreSSM is currently proven on linear time invariant LTI state space models and extensions like Mamba. It is not currently applicable to the massive transformer architectures, the GPT-4s, the Geminis, the Llama 3s, that dominate 95% of the current enterprise market.
So if you're a company heavily invested in the transformer ecosystem, this doesn't help you today.
Not directly, no. That's the big caveat. However, the researchers are acutely aware of this. Makram Chaheen, the lead PhD student, explicitly stated that applying CompreSSM to standard SSMs had to be the first step because this is where the theory is neat and the approach can stay principled. They chose their battleground carefully.
Which implies they're looking to expand its applicability.
Absolutely. The team is already looking to push the CompreSSM algorithm further into matrix value dynamical systems, which are used in linear attention mechanisms. If they succeed there, that would be the bridge, bringing in-training dynamic compression directly to the transformer architectures that underpin the world's largest AI systems. That would be the ultimate game changer.
So it's a huge leap for SSMs with the potential to then jump to transformers. That changes the timeline for widespread impact significantly.
It does. It means the current success is a proof of concept for a much broader ambition.
Okay, so let's zoom out a bit for our final thoughts. If this kind of efficiency becomes widespread, what's the macroeconomic impact? Will CompreSSM actually cool down this massive data center boom, or will it just accelerate something else?
That's a fascinating question, and it brings us to something called the Jevons paradox. Historically, when a resource becomes more efficiently used, the overall demand for that resource actually increases rather than decreases.
So if AI becomes cheaper and faster to train, we don't necessarily use less compute, we just find more ways to use AI.
Exactly. Think of it this way. If it becomes dramatically cheaper and easier to develop and deploy high-performing specialized AI models, then every company, every industry will want to embed AI into everything. Your car, your toaster, your pacemaker, your infrastructure, your medical devices. The total addressable market for AI applications explodes.
So while individual models become more efficient, the sheer number of models and the breadth of their deployment could still lead to a net increase in compute demand, albeit in a more distributed fashion.
That's my read. It could mean fewer monolithic data centers, but a massive proliferation of smaller, localized AI deployments. The hyperscalers might still grow, but their growth won't be the only story. It opens the door for a much more diverse, distributed, and possibly more resilient AI ecosystem. It's a shift from AI as a centralized utility to AI as an embedded, ubiquitous intelligence.
That's a powerful vision. So, a few key takeaways from today. First, the train big, shrink later model is fundamentally broken, unsustainable, and locks out innovation.
Second, CompreSSM offers a radical alternative, allowing models to self-optimize and shrink during training, thanks to a clever control theory hack.
Third, this breakthrough is supercharging state space models like Mamba, making them incredibly fast and efficient, posing a real threat to the transformer's dominance.
And finally, this paves the way for physical AI, intelligent, compact models running on edge devices, democratizing AI and dramatically reducing operational costs for businesses.
Thinking about this, if AI becomes so efficient that it can run on almost any device, anywhere, what new ethical considerations arise when every object around us potentially has advanced intelligence embedded within it?
And if the Jevons paradox holds true and demand for AI compute skyrockets due to this efficiency, what does that mean for the global energy footprint, even if individual models are greener? Is more efficient always more sustainable in the long run?
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.